There. The following tutorial will introduce for you Dijkstra's algorithm and how it's used to find the shortest path between two nodes in a network. So, just to give a bit of background, it can look like quite an unwieldy algorithm, quite difficult. With a bit of practice, it's not very difficult at all. It's about labeling and being systematic. I'll show you the algorithm. I suggest you copy it and note it down, but we'll do the algorithm via examples. So Dijkstra, what's it about? Dijkstra, in this example, say it's telling you to start at A and end at G, and it wants you to find the shortest route to get from A to G. That's it, as simple as that. Now obviously, one could do trial and error. I could go 7 and 7. So there's one here of 14. Could I better that? Well, yeah, I could. I could go, for example, 4, 1, and then the 7. So I could definitely better that and better that to 5 and 7, which is 12. Could I better that still? Well, yes, I could. What about 3, 5, and 2? 3, 5, and 2 would give me a total of 10. That's even better still. Could I go even better? How about 4, 1, 2, and 2? 4 and 1 is 5, add 2 is 7, add 2 is 9. It looks like I've gone even better still. Now, obviously, I could spend all day just looking at the different cases and find the shortest one. In this particular case, it actually wouldn't take me that long. However, with more nodes, it could take me a very long time. Dijkstra's algorithm provides us with a routine method of programming into a computer or doing ourselves a way of finding the answer. Now, it's not necessarily intuitive what's going on during this algorithm, so I would just suggest learning it for the purposes of the exam and how to apply it without too much thought about why it works, because it's beyond the scope of the syllabus to actually understand what this algorithm is doing at each stage. Okay, so I'm going to start by showing you the algorithm, and here it is. I suggest you copy it down and we refer to it as we go through the examples. Just a couple of points to say, a couple of drawbacks of Dijkstra. It doesn't work if any of the weights are negative, and it wouldn't tell you what the maximum route is between two nodes in particular, so it doesn't work for those cases. I'm going to go through this algorithm but via the example rather than just list it out here. You can all copy that down and read it for yourself, but we'll go through its meaning via an example. And here is the example. Example 1, Dijkstra's algorithm. The first thing you do is you start off at your starting vertex, which is A. There will always be a box drawn for you in the exam, and you fill in the box as I'm going to show you. A. You ask yourself, how far away is A from itself? And it is itself, so it's no distance away from itself. And you label that your first permanent label. So here is how far the vertex is away from A, and this here, you label it when you're certain that is the distance it is away from A, the shortest it can be. Okay, let's just look at Dijkstra next. Dijkstra says assign temporary labels to all the vertices that can be reached from the start. So, what can be reached from A? Well, B can, D can, and C can. Now, how far would B be from A? Well, it would be a distance of 4. So assign a temporary label for now. D would be 7 away from A, and C would be 3 away from A. What does the algorithm says next? You assign temporary labels and you add the correct order label. It says assign labels to vertices that can be reached from the start. We've done that. Select the vertex with the smallest temporary label and make it permanent. So which is the smallest out of 4, 7 and 3? Well, 3 clearly is. So this, we assign that as a permanent distance 3 away from A, and we're going to call it number 2. This is the second that we've assigned a permanent label to. Okay, let's have a look back here. Put temporary labels on each vertex that can be reached from the vertex you have just made permanent. The temporary label must equal the sum of the permanent label and the distance from it. If there is an existing temporary label at a vertex, it should be replaced only if the sum is smaller. Okay, let me show you what that means. You start from your new permanent vertex and you label everything that you can get from that. I can get to E from that in an extra 5 plus the 3 I've already got to C in, so the distance from E to A must be 5 add the 3, which is 8. I put that as temporary working. I could also get to D from C. D would require an extra 3 on top of the 3 I already got, so it would be a 6, and that's an improvement on 7, so I cross the 7 and I put a 6. Is there anything else I can get from C? No. I've got E and I've got D, that's it. Okay, now I look for which is the smallest out of all my temporary labels. 4, 6 and 8. The smallest is clearly the 4, so I'm going to assign that a permanent distance of 4, that's its final distance, and that's going to be number 3 that I've permanently labelled. Okay, at this point, this is my new permanent label here, so I've had that permanent and this is my third permanent label. I look at everything that could be reached from B and assign temporary workings for the total distances that those points are from A. F can be reached from B with an additional 4. On top of the 4 already to get to B gives me a temporary working of 8 for F. I can also get to D from B by adding an extra 1 on top of the 4, which would give me 5. This is an improvement on 6, so I'm going to write 5 in here instead. Is there anything else I can get from B? Well, no, just F and just D. I look at my temporary labels, 8, 5 and 8, and I choose the smallest, which is the 5, fill that in as a permanent 5 now, and that is the fourth one I have made permanent. So I'm going to include D now. Okay, now at this stage, I look at everything that can be reached from the permanent label I've just created. I can get to F from here. Now, it's 5 to get me here, plus another 2 would actually get me to F in 7. So I'm going to cross out the 8 and change it to a 7. I can get to G from here in 5 plus another 7, which is 12, so I'm going to write that here as a temporary working. And I could get to E from here in 5 plus a 2, which is 7, which beats the 8, so I'm going to write the 7 there. Anything else I can get to, well, everything else is permanent, so that's fine as it is. The smallest out of my 7, 7 and 12 is 7, so I'm going to pick either of them. Let's just check the algorithm says that. Yes, I mean, if they are the same, then you just pick either one of them. So let's just say, for argument's sake, we're going to pick this one now. I'm going to make that a permanent 7, and I'm going to say that is the 5th one I've made permanent, and I'm going to highlight that because I've done that now. From this permanent, everything I can reach from here. Now, I can only reach a non-permanent of G. That would be an extra 2 on top of the 7, which would be 9. That's a definite improvement in 12, so write it in. Okay, what are my temporary labels now? I've got a 7 and a 9. 7 is better, so I'm going to write this 7 as permanent, and I'm going to say it's the 6th one I filled in, and circle it to say, yeah, I've made that permanent now. Everything I can get to from F now, well, I can only get to G in another 4, and 7 and 4 is 11, that's not an improvement. So the best I can do for G now is to say that's a distance of 9, and that's the 7th one I filled in. The algorithm says repeat until the finishing vertex has a permanent label. I now have a permanent label on the finishing vertex. Now, the key thing here about Dijkstra. To find the shortest path, I trace back from the end vertex to the start vertex, or I write the route forwards and state the length. What I do is I start off at the last vertex. I ended at a G. So here I am at G, and it took me a path, a total of 9 to get here, I'm saying. Did I take the 4, the 7, or the 2 to get here? Well, if I took the 4, that would have to be a distance of 5, and it's not. If I took the 7, that would have to be a 2, it's not. I must have taken the 2, because subtracting that 2, I get this 7 here, which is the permanent label. Okay, from here, did I take the 5? No, because that would have to be a 2 if I did. Or I took the 2. I took the 2 here because 7 take away 2 gives me 5. Okay, from this point D here, what did I take? I can't have taken that 7. I can't have taken the 3. I must have taken that 1 because 5 take away the 1 is 4. And lastly, to get from here to here, the only thing I could have taken is that 4. So I've retraced my steps, and I'm saying my actual path is A, B, D, E and G, and it's got a total distance of 4 plus 1 plus 2 plus 2, which is equal to 9. And hence we have worked out Dijkstra's algorithm. Okay, going to do one more example and then leave one for you to do yourself. Find the shortest route from A to the ring vertex, which is G in this case. State the route and the length. Okay, A. How far is A away from A? Well, it's 0 away. That's the shortest label here, so I'm going to call that a permanent label of 1. Having created that as a permanent label, I look at all the routes that could come out from A. I could get to B in 6, so I write 6 there. I could get to D in 18. I could get to C in 3. Out of all the temporary labels, 3, 18 and 6, I mark the smallest and make it a permanent label. So I'm going to say to C, that's permanent, and it's the second one I've labelled. Now, starting from this permanent label here, I go to all the nodes I can get to. I could get to F in an extra 10, which would be 13, or I could get to D in an extra 20, which would give me 23. There's no good in that. I'm not going to improve on 18. So I look at my temporary labels 6, 18 and 13. Which is the best? Well, 6 is. So I'm going to call that a permanent label of 6, and I'm going to say that was the third one I called permanent. From this permanent here, I look at everything I can get to from this point. I could get to E in an extra 5, so that would be 11. I could get to D in an extra 11, so that would be 17, which is an improvement on the 18. Could I get to anything else? No, everything else is permanent. So I look at my temporaries 11, 17 and 13. 11 is the smallest, so I write in a permanent label of 11, and I call that the fourth one that I've made 11. And I circle it just to know I've done it. From that permanent, I mark in everything I can get to from here. I could get to G in an extra 9, so that would be 20. I could get back to D that would be 24. It's not an improvement on 17. So I stop there. I look at all my temporaries, 17, 13 and 20. This is my smallest. I make it permanent 13, and it's the fifth one that I've made permanent. So now F is included. Okay, from F, I could go back to D in 1 extra, so that would be an improvement of 13 plus the 1 is 14. I could go to G in an extra 14 on top of the 13 I've got. 13 plus the 14 is 27, which is no improvement of what I've already got. So the temporary labels I've got left, what's better out of 14 and 20? Well, 14 is, so I'm going to call that a permanent 14, and I'm going to say that is the sixth one I've made permanent and circle it. From D, I could get up to G in another 17, which would end up being something like 31, not an improvement. So G, the smallest I can do with it is 20, and that is the seventh one I made permanent. Now it's all about retracing my steps. Ending at G, did I take root 9, 17 or 18? I had to take 9 because 11 and 9 gives me the 20. None of the others work. From E, did I take 5 or the 13? Well, I must have taken the 5 because 11 take away 5 is 6. And from there, I must have taken the root 6 because 6 take away 6 is 0. So my root, therefore, is A, B, E, G of total distance 6 plus 5 plus 9, which is equal to 20. Okay, to finish with, I'll put up an example for you. See if you can work out the answer. Pause the video, then I'll put the answer up for you. Okay, pause the video now. And unpausing for the answer. Here's the following answer. I got that was the best route through. So the best route was A, B, E, H and I. And I got that was equal to 4 plus 2 plus 8 plus 3 plus 7, which worked out for me to be 24 in total using Dijkstra's algorithm.